Hello, we're looking at molecular geometry and the shapes of molecules. And so let's look at the first one, carbon dioxide. And whenever we're looking at these, we're looking at the central atom, these simple molecules. We're going to be looking at the carbon. And the first thing we want to do is determine the number of electron domains. So what's an electron domain? An electron domain can either be a non-bonding pair of electrons, it can be a single bond, it can be a double bond, or it can be a triple bond. Each of those corresponds to just a single electron domain. So a non-bonding pair, a single bond, double bond, or triple bond. So in carbon dioxide, CO2, the first molecule that we're looking at, we look at the carbon. There are no non-bonding pairs of electrons on it. It makes two double bonds. Each double bond is a single electron domain. So there are two bonding domains. So it gives us a total of 2 electron domains. That's the type of molecule that I'm going to refer to as being an AB2 molecule, where A is the central atom, and it's bonded to 2 different other types of atoms that we're just going to generically label B. And so when you have an electron domain of 2, that electron domain geometry is going to be linear. We're looking at the VSEPR theory to determine this. VSEPR stands for valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. So the electron domain is going to be linear. And that's describing the arrangement of the electron domains around the central atom. The molecular geometry is how the atoms are actually visualized, how they're arranged around the central atom. If there are no non-bonding pairs on the central atom, the electron domain geometry and the molecular geometry are going to be the same. So those 2 double bonds around that carbon are trying to minimize the repulsive forces between them by maximizing the angles between those electron domains. Valence shell electron pair repulsion theory. We understand how two electrons can go in the same orbital. They do that by pairing their electrons, by having opposite spins. Those electron pairs will now repel each other. And so they're trying to get as far apart from one another as possible on an angular basis. And so by making that molecule become linear, those electron domains linear, you maximize the distance between them, the angle between them, and you minimize the repulsive forces. So that bond angle is 180 degrees. It's also a hybridization type called SP, and we'll talk about hybridization a little bit later. It turns out that looking at the central atom, if you set yourself down on that pico scale and look out toward the atoms that are bonded to it, you see the same thing in both directions. While both of those bonds are polar bonds, if you think about vector analysis, they're exactly opposite one another when looking at that central carbon, so they cancel one another out. So this would wind up being a non-polar molecule. Some of these topics we'll be talking about in this early on in this chapter, some of them later on. I'm sort of filling this completely in as we go along. BH3, there's the Lewis structure for boron trihydride. It's an adequate Lewis structure. Boron is something that's actually electron deficient here. We don't have an octet around it, but that's all right because we can only show 6 electrons in this Lewis structure. And the point I'm trying to drive home here is just looking at the molecule, the Lewis structure of the molecule, may or may not give you what the electron domain geometry or molecular geometry are. So the first thing you need to do is count up the number of electron domains. Once again, there are no non-bonding pairs on the central atom. It's made 3 single bonds. Each single bond is worth an electron domain. So that means we have 3 bonding electron domains, so we got a total of 3. If we got 3, that would be a type of hybridization that we call sp2. Just ignore that for now if you haven't talked about hybridization yet. We got a central atom A that's surrounded by 3 different atoms. They're all hydrogen. But it's surrounded by 3 atoms that are all hydrogen, so we'll call that an AB3 type molecule. And so even though you look at this and you go, oh, the bond angles are 90 degrees. Well, you got 2 90-degree angles if the way this is drawn, and then you got 180 degrees. And so typically we're going to want those angles to be close to being equivalent. And so we can actually make those angles be equivalent if instead you visualize this molecule like this, where those bond angles now are going to be 120 degrees. And that's an electron domain geometry that we refer to as being trigonal planar. Trigonal planar. Now, all 4 atoms are found in the same plane. They lie in the same plane. And there are 3 angles in there. And those 3 angles are all identical. They're all 120 degrees. So the electron domain geometry in BH3 is trigonal planar. The molecular geometry is also trigonal planar. Those 2 will be the same if there are no non-bonding pairs of electrons on the central atom, and that's the case here. The next one is sulfur dioxide. Sulfur dioxide. The first thing you do is count the electron domains. We now have a non-bonding pair of electrons for the first time on a central atom in the examples that we're looking at. And we've got 2 double bonds. Each double bond is a single electron domain. So that means, once again, we have 3 electron domains around the central atom. If there's 3, that makes it sp2. It also makes it a trigonal planar electron geometry. This is a type of molecule that I'm going to refer to as being AB2E. It's a central atom with 2 atoms around it plus a non-bonding pair of electrons, which I'm going to denote with a capital E. So for the first time we now see a non-bonding pair of electrons on the central atom. That means the molecular geometry and electron geometry, domain geometry, are not going to be the same. Because the molecular geometry only takes into account those atoms that we can actually see. And so, even though that's a legit Lewis structure, it follows all the rules, because of that non-bonding pair of electrons on that central atom, that sulfur, they're repelling those 2 electron domains that make up the double bonds. And so, if we look at just the atoms, this is a shape that we're going to refer to as being bent. Bent. And that bond angle is actually going to be a little bit less than 120 degrees. And that those non-bonding electrons are more repulsive than any sort of bonding electron domain will be. And so it makes that angle be a little bit less than 120 degrees. The next molecule, CH4, is not carbon tetrahydride, although you might think that would be an okay name. It's a carbon-hydrogen molecule, which qualifies it as being an organic molecule, something that we call methane. The central atom is that carbon. It's got no non-bonding pairs of electrons on it. It's bonded to 4 hydrogens. That means it's got 4 electron domains. And so we could call this an AB4 type of molecule. And so when it's got 4 electron domains, the hybridization is going to be something called sp3. And the electron domain geometry is going to be tetrahedral. Tetrahedral. it may look like it's got 4 bond angles that are 90 degrees when we look at it, but that's thinking the molecule as only being in 2 dimensions. It really occupies 3-dimensional space. And so, in so doing, it can make a 4-sided pyramid, if you will, or tetrahedron. And so the bond angles are actually 109.5 degrees. And so those are large angles then are 90 degrees. So by taking that 3-dimensional shape, it can have these bond angles of 109.5 degrees and minimize the repulsive forces, as opposed to in the linear configuration where they would all be 90 degrees. And so this is a molecular geometry that we refer to as being tetrahedral also, because there are no non-bonding pairs of electrons on the central atom. So the electron domain geometry and the molecular geometry are the same. The next Lewis structure is one of the compounds called ammonia. We count up the number of electron domains. There's a non-bonding pair. Then there are 3 single bonds, each worth a single electron domain. So we've got 4 electron domains. If it's got 4, it means it has a sp3 hybridization. It's a type of molecule that I want to call an HB3E. Central atom A, 3 atoms generically labeled B around it, and a single electron non-bonding pair of electrons that we'll call E. So if it's got 4 electron domains, that electron domain geometry is always going to be tetrahedral. This molecule is not flat. All those atoms do not lie in the same plane. It still has that 3-dimensional structure of the tetrahedron that we saw in methane. Except now, one of those positions on the tetrahedron is not occupied by a 4th hydrogen. It's actually occupied by a non-bonding pair of electrons. And so, I can't draw a picture of that on this tablet, and you might want to look at your book, get a picture of it, or get a set of models out. But this is going to be a trigonal pyramid, or a trigonal pyramidal molecular geometry. And that's going to form a pyramid with 3 sides and a base to it. And those bond angles are going to be a little bit less than 109.5 degrees. Once again, that non-bonding pair of electrons exhibits a greater repulsive force than do electron domains in a bond, and so it scooches down those bonds a bit. H2O, water. The oxygen has 2 non-bonding pairs of electrons. It's got 2 single bonds, each worth a single electron domain. Once again, we got 4 electron domains. That means it's automatically an sp3 hybridization. You could say it's an AB2E2 type of molecule. That the central atom oxygen is bonded to 2 hydrogens. That's what I'm calling the B2. And this time it's got 2 non-bonding pair of electrons on it, or E2. If it's got 4 electron domains, that electron geometry is always going to be tetrahedral. And although that bond angle looks like it's 180 degrees, remember these molecules aren't constrained to a 2-dimensional shape. We're still looking at from that tetrahedral electron geometry to begin with. And so those 2 non-bonding pairs of electrons are going to push the hydrogens away from it. And so that bond angle is even going to be a little bit smaller than the bond angle that we see in ammonia, which is smaller than the ideal bond angle of 109.5 degrees in a perfect tetrahedron. Ammonia is probably about 170 degree bond angle, and the water is about 105. But this is a molecular geometry or shape that we're going to refer to as being bent. It's going to be bent. And because it's bent, water winds up very much being a polar molecule. Likewise, ammonia, because of that non-bonding pair in its shape, will wind up being polar. Methane is nonpolar because all the positions around the tetrahedron are the same on the exterior. SO2, because it's a bent molecule, that makes it become polar. And the trigonal planar BH3, all the positions were equivalent. It was nonpolar. I left those out as we go along. I want you to note the difference between the bent and SO2 and the bent and H2O, water. They start out from different electron geometries. Trigonal planar versus tetrahedral. And hence the bond angles wind up being different. They're both bent, but they have different starting points, if you want to think of it that way. PCl5. We see an example of a Lewis structure where the octet rule is not obeyed, and there are actually 10 electrons around the phosphorus. But that's all right, because it's now in the n equals 3 sublevel. And so, in an equal 3 shell. And so, we've got no non-bonding pairs of electrons. We say have 5 single bonds, or 5 electron domains. That gives us a total of 5 electron domains. This is a type of hybridization that we call sp3d, where we now have these 3D orbitals that we can use to help make that extra bond. The type will be AB5, and the shape electron domain that this particular configuration will give us will be something called a trigonal bipyramid, where it's a trigonal bipyramidal electron domain geometry. It's 2 3-sided pyramids, but base to base. So once again, look at a picture in your book, or look at some models to try to visualize this. Since there are no non-bonding pairs of electrons on the phosphorus, the molecular geometry and electron domain geometry are the same. So it's trigonal bipyramidal. And it turns out there are actually 2 different bond angles in this configuration. There are equatorial atoms and there are axial atoms. The axial atoms you can think about as being like the North and South Pole if you want. And the equatorial are around the center of the atom, the equator. There are 2 axial atoms and there are 3 equatorial atoms. So if you look at between an axial and an equatorial, that bond angle is 90 degrees. And if you look between the equatorials of each other, they're 120 degrees. And so if I drew this a little bit differently, you might see that here are my 3 equatorial. They're perpendicular to the chlorines and the phosphorus that are vertical. And so each of those have 120 degree bond angles, whereas the bond angle between the chlorine that's axial, and which is that chlorine, versus an equatorial chlorine is 90 degrees. The next one, SF4, sulfur tetrafluoride. We've got 1 non-bonding pair of electrons. We've got 4 single bonds. That gives us 4 bonding electron domains. Total of 5. This 5 is sp3d. But now we have an AB4E type of molecule. If it's 5 electron domains, it's trigonal bipyramidal. But now we've got a non-bonding pair of electrons. And the question is, where does it go? And so I've got a sulfur that has these fluorines around it. And where does that non-bonding pair of electrons go? Turns out it actually goes on the equatorial position as opposed on the axial position. Why? Valence shell electron pair repulsion theory. In that if it were in axial position, that non-bonding pair of electrons would have 90 degrees between all the bonding electrons that are close to it. Whereas here, yes, there's 90 degrees between this equatorial and that axial position, but now we got this 120 degrees, ideally, between the non-bonding pair and the other equatorial fluorines. So really this molecule sort of scrunches up a little bit, and so the bond angles are actually a little bit less than 190, less than 120. And this is a type of molecular geometry that we refer to as being a seesaw. So if I redraw that molecule like this, that non-bonding pair of electrons will sit up right there. And now you can sort of see the seesaw configuration. Those are the legs of the seesaw, and those are the ends where little boys or little girls sit to go up and down on their seesaw. The best thing to do is to look at some real pictures of these molecules, and we'll try to do that in another video, but this is sort of a nuts and bolts way of looking at these particular electron domain and molecular geometries, and we'll have one more page of this to look at in another video. Thanks for listening and watching.